So our lesson today is about this thing called the binomial expansion triangle. Sometimes it's called Pascal's triangle. And it turns out that this sort of arrangement of numbers is connected to a lot of other areas of math and a lot of other things that we can do. For today, I'm really just going to be focusing on sort of the basics of what this thing is. And sort of by the end of this lesson, our goal is going to be able to take a binomial and raise that to a fairly large power and do it relatively quickly. Now, this lesson is something that I could teach very directly, but I really enjoy allowing students to get a chance to sort of like see where it comes from and sort of find it on their own. So in the beginning of this thing, we're going to do some exploration, and then we're going to turn that into some direct instruction. So here's that exploration that I just mentioned. What I'd like you to do is pause the video and take each of these binomials that's raised to a different power, right? The first it's raised to a 0 power, then the first power, second power, third power, fourth power. And I'd like you to sort of expand all of those things out, write them out fully. And I'm hoping that in doing that, we're going to sort of see a pattern, something that emerges from this. So the top three should be really easy. Why don't you do those and then check in, and then we'll work through the other two as well. So that first one, again, should be really, really straightforward. When I have a plus b raised to the 0 power, we know that any non-zero thing raised to the 0 power is going to be 1. So I've got 1 there. Yay. The second one is also pretty trivially easy. It's a plus b. When I raise that at the first power, it's still going to be a plus b. Now, for something that I'm going to do later, like the coefficients are going to matter. So I'm actually going to write this as 1a plus 1b, just because I'm going to want to draw attention to the coefficients later. So we'll get there soon. In the next one, we've got a plus b squared. You guys have done enough polynomial multiplication. You guys should know that when we do a plus b times a plus b, whether you use FOIL or a box method or whatever it might be, you should wind up with 1a squared plus 2ab plus 1b squared. Now in this next one, when I'm asking you to do a plus b cubed, right, my hope is that your immediate thought is, hey, I just did a plus b squared. All I really need to do is take that thing that I did before, a squared plus 2ab plus b squared, and multiply that by a plus b. I have sort of a specific method for how I would encourage you guys to do that, but if you'd like to pause and just do it on your own, that's totally fine. For the purposes of this video, I think the thing that makes sense is for us to think about, I'm going to need to distribute the a to all of these things, and then I'm going to need to distribute the b to all of these things. So I'm just going to sort of write that out so we can see it here. I'm going to do a times this whole thing, a squared plus 2ab plus b squared. And then I'll also do b times a squared plus 2ab plus b squared. So when I do these things, when I distribute that a through, I'm going to wind up with a cubed plus 2a squared b plus ab squared. Okay? When I distribute the b through, I'm going to get similar things, and I'm actually going to sort of line them up here, right? When this b multiplies to the a squared, I'm going to get a squared b. So I'm going to put 1 a squared b here so that you can sort of see how it lines up with the a squared b term that we got from the other one. Similarly, when that b gets to the 2ab, we'll have plus 2ab squared. And then finally, when the b gets all the way to the b squared at the end, we'll wind up with b cubed. And because of the way I've lined these things up, I can sort of just add these two things together and find that a plus b cubed is 1a cubed plus 3a squared b plus 3ab squared, and finally plus 1b cubed. Okay? All right, so now I'm going to ask us to do this thing one more time, right? A plus b to the fourth power, we should be able to do this a cubed plus 3a squared b plus 3ab squared plus b cubed, and just multiply that by one more a plus b. And so if you haven't already done that, pause the video, multiply that out. I'd recommend that you do it, using the way that I did here. So hopefully you've done that now. When I distribute the a to this whole thing, 3a squared b plus 3ab squared plus b cubed, I wind up getting a to the fourth plus 3a cubed b plus 3a squared b squared plus ab cubed. And I'm not going to write the whole thing out, but when I do b times this whole thing, I'm going to wind up with, let's see here, it'll be a cubed b. And then when I do the b times this one, I'll wind up with 3a squared b squared. And the b times this one is going to get me 3ab cubed. And finally, the b with this one is going to get me b to the fourth. When I add all of these things up, I wind up with 1a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the fourth. Now, I want to be really clear. The purpose of today's lesson is supposed to be about a shortcut. So I would love to be in a place at the end of this video where you never do this again, where we see the thing that I want us to see, and then we sort of appreciate and enjoy the shortcut that we have. So the next step that I'm going to ask you guys to do is I want you to go back and circle all of the coefficients here. Like, make sure that you can really clearly see all of the coefficients, right? So you should notice you had 1 coefficient in the first one, you had 2 coefficients in the next one, you had 3 in the next one, you had 4 in the next one, you had 5 in the last one. What I'm going to show us now, what we're going to do now is we're going to arrange all of these things into effectively like a pyramid or a triangle of numbers. So here we go. That expansion thing that we had 1 as the coefficient in the first one. It had a 1 and then another 1 in the next one. The coefficients in the second power one that we did were 1, 2, 1. The coefficients in the third power we did were 1, 3, 3, 1. And the coefficients in the fourth power one that we did were 1, 4, 6, 4, 1. Now, maybe you've seen this before. Maybe you've heard that this thing is called Pascal's triangle and that it was discovered by Blaise Pascal, a French mathematician. And that's not entirely accurate. Blaise Pascal was a French mathematician. He sort of wrote about this triangle in the 1600s, but there are sort of records of this having been discovered and seen and written about by Indian mathematicians, like 450 BC, by Chinese mathematicians in like the 1100 AD range, by Italian mathematicians 100 years before this, by Iranian mathematicians a few hundred years before this. So this is definitely not something that was discovered by Pascal, but because he lived in Europe and there were a lot of things spreading all over the world from Europe, not all of which were amazing, in the 1600s, that's the name that's gotten stuck. I will generally try and refer to it as the binomial expansion triangle as opposed to Pascal's triangle, just to make sure that we indicate that not all of mathematics originated in Europe. Now, there are a lot of patterns in this triangle, and I'm going to hold back on showing you a lot of them because I really don't want this video to be an hour long. The thing that I really want to focus on is, could we find out what the next row of this thing was? Like, it would be amazing if I could figure out what this next row is. Now, one way to find out what the next row is would be for us to do a plus b to the 5th power, and then, like write down those coefficients, but I don't know. I don't want to do that. That last section of this video took way too long. But what I hope you guys notice is anytime there's one of these numbers like this 4 seems to be the sum of the 1 and the 3 that are diagonally above it. This 3 is the sum of the 2 and the 1 that are diagonally above it. This 4 over here is the sum of the 3 and the 1 that are diagonally above it. Which means that what we can do is it looks like we can always put 1s on the outer edge of our triangle, and then inside we sort of put together the 1 and the 4 to give me 5. I can put together the 4 and the 6 to give me 10. This next number here would be 10, and this next number would be 5. Pause the video for a moment and make sure that you can write down for yourself what the next row of Pascal's triangle would be. Sorry, the binomial expansion triangle would be. We should have here 1, 6, 15, 20, 15, 6, 1. And we can do it again. Like, pause the video one more time, make sure you can get the 7th row of Pascal's triangle. Binomial expansion. Man, I spent a lot of years calling this the Pascal's triangle. So 1, 7, 21, 35, 35, 21, 7, 1. Now, in the rest of the video, I want to talk about how we use this to shortcut processes like this. Like, how do I actually use this knowledge to make these problems, go more quickly and get through them? And the secret here is to remember that this triangle is made up of the coefficients in these expansions, okay? So, for instance, if someone had asked me, and I'm not going to do the whole thing here, if someone had asked me to do a plus b to the 7th power, I would know that my first coefficient was going to be 1 from right here, and that would be 1a to the 7th. Plus, I would know that my next coefficient would come from right here. It's going to be 7, and that would be a to the 6th power b. Because what happens is these are my two things. I have a and I have b, and these powers, as you saw previously, those powers of the first thing are just going to keep decreasing as we go along. Right? To show you one more of these, my next coefficient would be 21. And I would have a to the 5th power, because my powers are going to keep dropping, and the b would go up to being a 2nd power. So like I said, the rest of this video, we're going to go through examples of this and practice a few of these things. I guess before I should go to the next slide, I should mention there would be 1, 2, 3, 4, 5 more terms in this thing. I don't know that it's instructive for us to go through all of those right now. So let's get to these other examples. All right, so here we have a concrete problem, right? Use the binomial expansion triangle to expand 3x minus 2 raised to the 4th power. So the first thing we need to do is we need to think and to remember what the row of the binomial expansion triangle is that has a 4 in it. It starts with 1, and then it goes 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So the row of the binomial expansion triangle that we want is this one right here, the one that has a 4 in it. It's worth noting the first row in the triangle is often called the 0th row because it comes from the binomial to the 0th power. So this is the 0th row, 1st row, 2nd row, 3rd row, 4th row. So even though it looks like it's the 5th one, we're going to call this thing the 4th row. So the coefficients here, just so we can write them down, 1, 4, 6, 4, 1. So now the next step for us to do is to expand this thing out. Now I could expand this thing like this, all out on one giant line, but this is really hard to work with. You may notice I did put these coefficients here just like I said I would. I did take these powers, 4, 3, 2, 1, 0, and sort of decrease them as I'm going along, but as you can tell, this is a giant long line of math, and it's really hard to work with this way. So there's another way that I like to organize my work on these. So I'm going to erase all of this, and I'm going to show you guys sort of how I like to structure this to make it a little bit easier to work with. Instead, I like to think about this term by term. I think, one of my terms is going to have a coefficient of 1. One will start with a 4, one will start with a 6, one will start with a 4, and the last one will start with a 1. And then, I've got all this space next to it. In that space, I can write in, hey, that first coefficient, it would use the first term of the binomial, 3x, raised to the 4th power, and it wouldn't have any factors of -2, okay? For this one, I would have 3x to the 3rd power, because the powers are supposed to drop, and the other term is supposed to start increasing. Oops, that should have been a 1 here. Then this is 3x squared, and this will be -2 squared. This would be 3x to the 1st power, and -2 to the 3rd power. And finally, we get all the way to 3x to the 0 power, where I'm not using the 3x term at all, and it's all coming from the -2. Okay. The next thing that I do is I begin to simplify each of these things, okay? So for instance, this first one here, I'd have 1, and then I'd have 81x to the 4th, and I'd have 1, which means that my first term is going to be 81x to the 4th. Okay? For the next one, same thing. I have my coefficient of 4. When I have my 3x raised to the 3rd power, it's going to give me 27x cubed. And then my -2 to the 1st power is going to give me -2. When I multiply all of those things together, this is going to wind up being -216x cubed. I'm going to go ahead and pause the video and just write out the rest of these, just so that the video isn't ridiculously long. But you should pause the video and make sure that you can work through and figure out what all of those are. So now that I know what all 5 terms in this expansion are going to be, I can just write them down and sort of add them up. This means that 3x minus 2 raised to the 4th power is going to be 81x to the 4th minus 216x cubed plus 216x squared minus 96x plus 16. I know that this is still not a fast process, but I think that you will find that this is certainly quicker and a little bit nicer than trying to multiply this thing out via polynomial multiplication all the way up to the fourth power. Now, another thing that's neat about this binomial expansion triangle thing is that there are also ways to ask these questions that don't make them take forever. So for instance, this example, find the term including x to the fifth in the expansion of 2x minus 5 to the seventh power. So this problem is not asking for the entire expansion, it's just asking for this term. Okay, so thinking back to what we did before, our first step here needs to be, let's figure out what the seventh row of, like this 7 up here, let's figure out what the seventh row of Pascal's triangle is. So, you can go back and look at your binomial expansion triangle, look at it and see if you can identify which row is the seventh. So hopefully you found that it was this one. So this is our seventh row of the binomial expansion triangle, and according to the way that I was recommending that you guys structure this, is we're not going to try and do this all in one super duper long line. We're just going to be looking at this row by row. 1, 7, 21, 35, 35, 21, 7, 1. Now remember, we're not going to do this whole thing. We just have to find the term that includes x to the fifth. So let's start writing down what these things, we're not going to do all the work, but let's start writing down what these things would be. This 1 would use the first term 2x to the seventh power and the negative 5 to the 0th power. Well, I mean, that's not what I want. I wanted x to the fifth. This is going to be, no, that wasn't the one I wanted. Let's try the next one. This next one would be 2x to the sixth times negative 5 to the first. Well, again, like right away, I can tell that one's also not the one that I wanted, because that's going to be x to the sixth. This next one, though, when I do 2x to the fifth, this would be negative 5 squared. This one right here is going to wind up getting me that x to the fifth I want, which means for the purposes of this problem, I really don't care about the rest of this. All I have to focus on is what's happening in this term right here. Okay, so expanding these things out, that coefficient of 21 is going to be 21. The 2x to the fifth is going to be 32x to the fifth. The negative 5 squared is going to be 25. And then when we multiply all of those things together, you'll wind up with 16,800 x to the fifth. And there we go. In just about 2 minutes, we were able to figure out what one specific term was in an expansion that would absolutely have been terrible if you were asked to do the whole thing. All right, so in this last example, it's going to be really similar to the previous one. This is going to be another quick one. I'm not going to ask for the whole expansion. I'm just asking for the coefficient of x in the expansion of this thing. So similar to the previous one, all I want to know is if you did expand this all the way out, and if you found the term that only had a plain x in it, not an x squared, not x cubed, not x to the fourth, just the x, what would the coefficient of that be? Okay, so I would encourage you, pause the video, figure out the row of the binomial expansion triangle you need, set this up, and figure out which one of these things it is that you're working with. So when you refer back to your triangle from before, you should know that the row of the binomial expansion triangle that you're looking for is the row 1, 5, 10, 10, 5, 1. So then we're going to set ourselves up vertically the way that I've showed us to. 1, 5, 10, 10, 5, 1. And then we start looking and thinking. We go, I want to find the coefficient of x, like just the plain x alone. Well, this first one is going to be x to the fifth. That's too much. This is going to be x to the fourth. That's still too much. In fact, I might not even need to write these. I can tell this one is going to be x cubed, x squared. This one is going to be x to the first power. This one down here would be x to the 0 power. I hope you guys can see pretty clearly. This is not going to give me x alone. None of these are going to give me x alone. It's going to be this one right here that's going to give me the term I'm looking for. Okay, so we just have to figure out, what do I pair with this? This is the coefficient 5 times x to the first power times the other term, negative 3, raised to what power? Well, one option is that we could go back and say, well, this should be a 0 power first, second, third, fourth, and this would be 4. The other thing you guys may have noticed is that these exponents here, the 1 and the 4, always seem to add up to whatever the power of the binomial is that we're working with. So in expanding this is going to give me 5x and then 81. And so when I multiply these two things together, these three things together, I'm going to get 405x. Now we need to make sure we answer the question. It said find the coefficient of x. So the answer to our question is 405. The coefficient of x, if I did this whole expansion, would be 405. Hopefully that all made sense. If you've got any questions, make sure you send them over to me. I'd be happy to help.